So this goes in a pocket. And this goes anywhere on your. If you need help, I'll just.
Yeah.
Okay, should be good. Okay, and are you okay with your talk being recorded?
Yep.
Yep. Okay. What's up? Great. Thank you.
Oh yeah, it's gonna be. Otherwise, we're gonna go way over. All right, so our last talk is by Philippe Guyenne. He's going to tell us about modeling and simulation of wave propagation and attenuation in sea ice.
Thanks, John. All right, so thanks everyone for sticking around till the end. First, I would like to thank the organizers, in particular Fabio and Catherine, for the invitation. It's great to be back in Toronto and see some friends and colleagues. So I'm going to talk about waves in sea ice. It's a compilation of results obtained with a number of collaborators, including Emilian and Catherine, who are in the audience. All right, so here's my share of pictures. So on Tuesday, Olga gave a related talk. She gave a great introduction for why it's interesting to work on waves in sea ice. So of course, I'm not going to repeat all that, but let me just reemphasize the fact that sea ice comes in many different flavors. For example, grease ice, pancake ice, ice flows, pack ice, among many other configurations. And so each with its own geometry and properties. And because of that, it's a major challenge to model such a complex medium. All right, so wave-ice interaction is a two-way process. So on one hand, sea ice can affect waves through multiple scattering, turbulent dissipation, elastic stresses, and so on. And therefore, at large scales, on average, you see a fast exponential-like decay of the incident wave energy as you move into the ice field. On the other hand, waves can also affect sea ice. The waves can move the ice, can deform the ice, can break the ice. And therefore, at large scales, they control the flow size distribution. So in this talk, I'm going to restrict myself to just one aspect of this problem, the first part. In fact, just a small subset of that first part. But hopefully the models that we developed and their predictions may have implications for the second aspect. All right, so that's the mathematical formulation that I'm going to use. The potential flow formulation for water waves. And again, you already saw many times these equations this week. So very briefly, just to make sure we're on the same page for the notation. Eta, that's the surface deformation at the top. Phi, that's the velocity potential. It satisfies the Laplace equation inside the fluid domain. And then you have two boundary conditions at the top, a kinematic and a Bernoulli condition. So the last one, that's a force balance equation. So the sketch at the top is to give you an idea about the setup. But in fact, I'm going to assume deep water, so infinite depth for most of what I'm going to talk about here. And so it's a challenging problem, of course. And to add the difficulties, we have a new feature, which is this term P in red, which is the pressure exerted by the ice cover on the fluid surface. And of course, a question you may have is, what is this pressure term? So of course, there are a lot of assumptions behind this formulation. For example, so we assume that the ice cover is a thin elastic plate sitting on top of the ocean surface. The ice plate bends in unison with the ocean waves. So basically, that means that the water surface and the ice cover, they coincide in this formulation. It's the same thing, the same boundary. I'm going to ignore any dissipative processes in this problem. So basically, what I just have in mind is changes in the wave dispersion or changes due to wave scattering because of the ice. Basically, that's all. I'm also going to assign a spatially dependent indicator function, f of x, to that pressure term. That is f being 0 when you have open water, and f equals 1 when you have ice. And in between is just going to be a steep transition. So it's kind of very similar to the order parameter phi in phase field models that one of the previous speakers talked about. So this is just for illustration down here. So in this example, we have 1, 2, 3, 4, 5 ice flows at the top and open water elsewhere. So that is going to be useful when we want to describe a fragmented ice cover.
That's badly out of scale, right? It's actually really thin. It looked like a heaviside function, but I mean, the dimensions are hundreds on the x-axis and 1 on the y-axis.
That's right, but this is just for the scale of f of x.
Okay.
That indicator function between
right.
0 and 1. It's just for that indicator function. Okay. But this is an example of the computation domain. Okay. Yes. Sorry about that. All right. So so we're going to include 3 contributions to this pressure term. So P1 here, that's inertia. P2, that's compression. And you can think about compression as anti-surface tension, because the difference is basically just by sign. And in fact, that reminds me that surface tension has been all over the place in many talks during this workshop. And that's also true here, all right, when we talk about free boundary problems. But the scales we're looking at are typically larger than the capillary scale that we're kind of familiar with. And P3 is bending or flexural rigidity. So these are 3 contributions. Note that all 3 of them are nonlinear in eta. And again, eta in my notation, that's the surface deformation at the top of the domain, basically the deformation of the ice. And the dots is to say that you can add more if you wish, given the complexity of the problem. All right, so there are 2 parts in this talk. Hopefully I can do it. The first part is focused on modeling. So we want to derive a reduced weakly nonlinear model in the context of a continuous ice cover. And the second part is going to be about simulations of the full nonlinear equations. So for the first part, we're interested in the asymptotic regime of wave packets on deep water. So something like that, which is motivated by field observations. And here I'm just citing a few references. And the main message is that the group structure of the waves seems to be enhanced in the presence of ice. And so that's exactly the setting where the NLS and the dist equations are relevant in the context of water waves. And here we want to derive a version of that with ice. Just for more motivation. So I'm not sure why I'm showing you this, but anyway, it's late in the afternoon, so just relax. In fact, that's the title of the video, is about relaxing. So this is what kind of waves you may have. I believe it's in the Arctic, and this is pancake ice. So it's very smooth, right? Compared to a more choppy sea state, say further south in the Atlantic. All right, so I guess I should stop this before we see some ads. All right, so done. All right, so just as a warm-up, so still part one, let's say P0, right? So standard waterway problem. So the starting point is the Hamiltonian reformulation of the equation that I showed you earlier. Again, as we heard in some previous talks, this Hamiltonian formulation has some nice structure, some nice properties that we want to take advantage of. So here the main variables are eta, again, surface deformation, xi, the trace of the velocity potential of the surface. You have the corresponding Hamiltonian. That's the total energy of the system. So you have a kinetic part and then a potential part due to gravity. And as Dave said, you can do this thanks to the introduction of the Dirichlet-Neumann operator. And in particular, you can use, yes? Just at the surface, ice cover, yes. To me, it's the same thing. So, so in this setting, first part, we have a continuous ice cover. And in the thin plate approximation, ice cover and water surface, it's the same thing. And the ice is taken into account by that P in the Bernoulli condition. So geometrically, it's the same boundary, but we add more forces in the Bernoulli condition. Elasticity, bending, things like that. Say one more time. So right now, P0. Yeah. Warm up. Yeah. Warm before ice. Yeah, sorry. Right now, just P0. But yeah, it's going to show up in the equation for Xi. So you have some additional pressure terms. All right, so because of that, we can use some powerful tools of Hamiltonian perturbation theory, where we can work directly on the Hamiltonian to obtain a reduced form. And so typically when you're in a weakly nonlinear regime, you want to do two things, right? You want to model the wave dynamics over large length scales and long time scales. You need to do two things, okay? So for the length scale, we just homogenize, so it's not too bad. For the time scale, it's a different beast. So I would like to spend more time on this. And again, it's very much in the spirit of what Alberto talked about in his talk earlier. So you can eliminate non-essential terms. And when I say non-essential terms, I mean here the non-resonant cubic terms by Birkhoff normal form transformations. So basically the purpose is that you want to push the asymptotics, you want to push the time of validity to a higher order. So indeed, free wave interactions, you can show that they are non-resonant for surface gravity waves on deep water. That means that you can eliminate the cubic terms by renormalizing the Hamiltonian. And interestingly, in this case, the normal form transformation is not your typical algebraic transformations. It's itself given by a Hamiltonian PD system. And the corresponding Hamiltonian flow is the transformation. Okay? And by the way, in this case, that PD system, the transformation, is a Burgers type system. And we can characterize explicitly this Hamiltonian flow and the corresponding Hamiltonian K3. So basically what you do is that you Taylor expand the Hamiltonian between two states, before and after the transformations. And then you impose that all the cubic terms from this expansion must vanish. And so if you do this, then this gives rise to this equation for K3 that you need to simplify, that you need to solve. And you can show that the solution, so K3, is given by this expression. And that was shown by Walter Craig and Catherine Sulem in 2016. All right, so and then in the end, so I'm kind of skipping details. In the end, you can derive the Hamiltonian disk equation for this problem for the wave envelope U, which is a slow function of space and time. So this is the corresponding Hamiltonian. This is the corresponding evolution equation. So on this line, you can recognize the standard NLS terms. So phase, advection, dispersion, cubic nonlinearity. On the next line, these are the additional terms due to dist. So higher order dispersion, higher order nonlinearity, including this non-local mean flow term. Now back to the wave ice problem. And we're going to choose the pressure P. Again, back to a previous question. That's really where we include effects from the ice. We're going to choose P to be given by P2 and P3. So compression and bending. And you see that the dispersion relation in this case is more complicated. Right? You have more parameters. In fact, it can be even negative, minus pk squared. So therefore, we need to be in a parameter regime where this does not happen, right? So that means that ice compression cannot be too strong. And that means also that, unfortunately, some cubic resonances are possible because of that. Okay, and therefore we need to take them into account in our perturbation calculation. And so basically what we do is that we split the Fourier space into a small resonant part and a very large non-resonant part. And we use the non-resonant part to find K3 in this case. So it's a bit technical, so I'm not going to say more than that. But just to summarize, the problem is also Hamiltonian in this case. Therefore, we can use exactly basically the same techniques.
Sorry, is there, can you go back to the slide? So is there a physical reason why you want to choose the dispersion relation not to be negative, at least in some